All right, now in chapter 8 here, we're going to turn to talking about the integers. The integers are a set of numbers that are the whole numbers and their opposites. Um, and so we have the whole numbers, which kind of depending on how your book defines it, we might just be talking about 1, 2, 3, 4, 5, and so on. Or sometimes we include 0 in that group as well. And we're also going to, when we talk about the integers, now include all of the negative whole numbers. So -1, -2, -3, and -4, and so on. And 0 is definitely in this set as well. So your book denotes this with a capital I. I will also sometimes denote this with a blackboard Z. So you might sometimes also see this notation for the integers. Either one is completely fine. The Z is definitely much more common. It comes from the German word Zahlen for integers. That's where the Z is. Just wanted to briefly touch on a little bit of the history. So on page 302 of your textbook, they have a nice little summary of brief history of the negative numbers. We talked about when we were talking about different numeration systems, we talked about how the Mayans were one of the first civilizations to use to have a symbol for 0 back in 300 BCE. And the first mention of a negative number came in 200 BCE in China. In 300 CE, Diophantus mentioned an equation 4x plus 20 equals 4, of course not using this same notation, and he mentioned that this was absurd because x would have to be equal -4, so which they didn't think was a number at the time, or didn't believe was a number at the time, I guess, or treat that way. A lot of development had to happen since then. 630 CE, there's a mention of negative versus affirmative quantities, and 1300 CE, a Chinese mathematician mentioned the rule of signs. That's right, sorry, that says rule of signs. I couldn't even read my own handwriting there. In an algebra text, which relates to zeros of polynomials. And finally, in 1545, Italian mathematician talked about negative roots of polynomials and clearly states a rule of negatives in his text. So so this is a little brief history of kind of the way we've come about finding these things would be through manipulating algebraic equations and seeing that in order to have solution, sometimes we need to introduce negative numbers. And that brings us to expand our set of numbers to include negatives, and that's what the integers does. Okay, so as far as models for such things, we already have a set model of the integers, of whole numbers, where I put, say, like 4 dots in a set, and that would model the number +4. In this model, one thing you can do is you can denote, you can use different colors to denote whether or not your elements are positive or negative. So here I might, if I put, your book uses red dots to denote negative numbers. So you might use this set model by using different colors or different shape to denote negative versus positive numbers. Of course, we can also use a measurement model. Now, for the first time, we're not just talking about a number line that starts at 0 and continues only in the right direction. It's going to go both directions, right? So we can start at 0 and move to the right. We can also move to the left, right? And here we use these numbers on opposite sides of 0. We sometimes call them opposites. So like 4 and -4 are opposites, 2 and -2 are opposites, with the idea that if you add opposites, you should get 0. Okay, so What we want to talk about is addition and subtraction using just integers. And so the models become a little bit different, or get a little interesting in this case, more complicated than we had with whole numbers. So if I take my set model and I want to say model 3 plus -4, here I have a set with 3 elements and I have a set with -4 elements in it, and I want to add these two things. Well, I can think of adding all of my elements to one big set. So I have 3 black chips and 4 red chips. And what happens is I can use opposites to pair things off and see what happens. So for instance, I can choose, I have 3, oops, I probably should have laid this out a little bit differently. I'm going to move one of those red chips so my picture looks a little bit clearer. Oops. Red chip. There we go. Okay, so I can move, I can remove, so every time I get a pair of opposites, they can we can think about removing them, or when I pair them off, they cancel each other out. So what I'm left with is just one red chip. So with these models, the idea is canceling, or opposite pairs cancel each other out. And I can use the measurement model to represent addition as well. If I wanted to add 3 and -4, I might start by moving to the right 3 units, and then from that point, I would move to the left -4 or 4 units, which means it's going in the -4 direction, and I would see that I would end up at -1. Okay, so your book defines addition in a super weird way. What they're trying to do here is they're trying to say, we basically defined addition on whole numbers, and now we're going to tell you about how you can extend that definition to integers. This is this is like a very this is one of the points where I'm like, okay, you guys, you've gone too mathematician-y for me. And I say that as like definite mathematician. Like this is completely useless way to do things, but they think they're being rigorous, so that's nice for them. Anyway, you can completely ignore this definition in my mind, but basically what the idea is, basically we know how addition works on the whole numbers. Now, using these 4 little axioms or points, this is how we're going to extend it when we have negative numbers. Don't worry about this definition. I just thought I would call your attention to that's what's going on here if you read that in the book. I want to see if there is a point here. Yeah, basically it tells you how to define when you have a negative number in terms of a whole number difference, and it's really silly. Okay, so properties though are going to be good to pay attention to. So now remember, we're talking about a different set here. We're talking about the set of all integers. I think I have a pointer. Oh, I just realized I have a pointer. That's great. So we're talking about the set of integers. And we want to talk about closure now with respect to this new set. This new set is closed under addition, right? If I add 2 integers in 2 elements of my set I here, I remain in there, okay? It's also commutative and associative, just like we would expect. There is definitely no doubt about the fact that there is an additive identity in here. 0 is definitely in the set. No matter who is talking about the integers, they always mean 0 is in there. And now what we did not have before, for sure, is the additive inverses. So we finally have a case where for any element that we take that's an integer, so any integer, there's a unique number that I can add to it, its opposite, so that we get 0. So when you say this in, when you translate this into an example, it's pretty obvious, like 2 is in the integers, so is -2. If I add 2 and -2, I get 0. Great. -7 is in the integers, so is 7. When I add -7 and 7, I get 0. Great. That's really all this is saying. It's saying we can do this for every single integer. It seems kind of silly, but we didn't have this before. And so here is again, we already talked about inverses with respect to multiplication. When we introduced fractions, we said, once we move to fractions, we're closed under inverses for multiplication. And now we're closed under addition when we consider the whole set of integers, but we weren't before because we didn't have those negative numbers. Again, it seems silly, but this is actually what allows us to solve algebraic equations. So again, this is kind of something you knew to be true, but it's actually much more powerful than you probably realize. And again, I think inverses are a really nice word to use and kind of thing to think about when you're introducing some of these concepts, because they really help us understand when we can cancel things and kind of understand that fact a little bit better. So for instance, what I'm referring to is this first theorem, which again seems obvious maybe when you see it, but why these things are true lies in this identity, in additive identities and additive inverses. It basically says if we have 3 integers, a, b, and c, so any integers at all, if I take a plus c, and I know that's equal to b plus c, then a has to equal b. And you basically say, hey, I know that to be true because I can just subtract c on both sides and I get a equals b. And that's exactly how this proof goes. It says, well, I'm assuming this thing that follows, I don't know. Oh yeah, sorry. I'm assuming this thing that follows if. I'm assuming a plus b equals b plus c. And then what I do is I add negative c on both sides, which I can do because it doesn't change the value since I'm doing it to both sides of the equation. And then using just associativity and additive inverses, then I get, and the fact that 0 is the identity, I get that a equals b. So that's what allows me to solve these equations. Another kind of basic theorem, but I thought I would bring up is that if we have any integer a, if I take negative a, that's just the same thing as a. And that can be modeled through this little diagram. So even if a is a negative number, so we can even assume a is negative, so it's represented by, like here it's a is -3. If I take -3 and I toss a negative, it becomes +3. If I toss a negative again, I get back to myself, to where I started. Okay. So as for subtraction, again, we could try to define it how we, and I think I can't remember if they do define, write out a definition explicitly from the whole number definition, but how they explain subtraction on the integers is through a couple different ways that we can understand it. So one is through looking at a pattern. Another is through the takeaway method, which is really close to kind of very similar model with adding opposites. Or we can also still use this method of understanding subtraction through the missing addend explanation. So what's new here is the idea of looking at a pattern. And so if I'm looking at a pattern, the reason why I have this now is because I know how subtraction works on whole numbers. So for instance, I know that 5 minus 4 is 1 and 5 minus 3 is 2. And basically, if I follow this pattern down and I just subtract something smaller each time, so now I'm subtracting 2, now I'm subtracting 1, notice that the answer, or what we're equal to, increases by 1 each time, right? So the pattern suggests that if I subtract 0, well, I should get 5, which I know to be true. And if I subtract, it's just following this pattern, if I subtract -1, it looks like I should get 6. If I subtract -2, it looks like I should get 7, and I can do this forever. So we could explain subtraction by following this pattern that we already have that starts with just whole number subtraction. That's one explanation. Another explanation, we can try to use our set method and, our takeaway method or our adding opposites. Both of these work really well with the set model of addition and subtraction. So for instance, if I have something like -4 minus -1, well, what I'm starting off here is with 4 red chips. And then what I want to do is I want to take away -1 of them. So I'm going to remove -1, and I see that what I'm left with is just -3, right? I'm just left with 3 red chips once I take away one of them. Okay, this model becomes a little bit more complicated when I deal with subtracting other negative numbers. So for instance, in these next two examples, so here I was taking -4 and I was just taking away 1 red chip. But if I look at the next example with -2 minus -3, well, I start off with 2 red chips, but I want to remove 3 red chips. And so we have to find a way around this. So that here's where we kind of have a divergence of ways we can think about it. We can have there's a very subtle distinction. So there's the takeaway method idea, and then there's the adding the opposite way of thinking about it. So with the distinction is when I think about the takeaway method, what I want to do is right now here for this representation of -2, I have 2 red chips, but I want to find a different representation of -2 that also has 3 red chips. So in order to do that, I'm going to toss in another red chip, but that's no longer -2. So I'm going to also toss in a black chip. Okay. And so now what's in the set still represents -2, but it's just a different representation. But it also contains 3 red chips. I can now throw away those 3 red chips, and I see that -2 minus 3 is +1. Basically, visually the same. We can think of this as the same thing happens, but another way of kind of thinking about this is instead of thinking of it as find another representation of -2, what I'm doing is I'm taking what was -2 and I'm going to add a bunch of opposites in. So I'm adding this pair of red and a black. So I'll further explain that in this next example. So we can kind of think of it as like adding 0. So let's look at that more in this next example 3 here. So for instance, if I take 2 and I want to subtract 5, well, I want to take away 5 black dots, but I don't have 5 black dots. So in the takeaway approach, what they would say is find a new representation of 2 that involves 5 black dots. What the adding the opposite approach tells you is, well, one way to do that is to pair off and every time you add a black dot, add a red dot because that adds to 0. So I want 5 black dots in here. So I'm going to put, actually, let me move this dot just so I have a little space. So I want 5 black dots in here. So I'm going to add 1, 2, 3, 3 black dots, right? And since I just added 3 black dots, I'm going to cancel those out by adding 3 red dots. It's really the same exact thing. You're really just kind of describing it differently. So now I have a representation of 2 and it contains 5 black dots. I can take away those 5 black dots and I see I'm just left with 3 red dots. So that means I'm left with -3. Okay, so different ways to use this set model to understand subtraction of integers. Again, you could use colors, you could use shapes, you could use a positive negative sign on these things. There's lots of different visual representations you can use to make this make sense. Last but not least, for understanding subtraction, we can still use our missing add-in approach. So remember, the missing add-in approach says if I take if I want to find a minus b, what I'm asking is what do I have to add to b to get a? Okay, great. A couple nice examples to look at. One thing to note is now when I put some sort of variable like a, when I'm talking about it and I say it's an integer, I don't actually know if a is positive or negative. So if I say a is an integer, like I do in this theorem, a could be positive or a could be negative. So that means if I see negative a, that doesn't necessarily mean that's a negative number. For instance, if I started off with a equals -3, like in this representation, then negative a is positive 3. Okay, so this is one little trick to keep in mind. This trips up students quite a bit. Don't let it trip you up. I think that's what's going on with, for example, number 21 here at the end of this section. I think it's related to this concept. So maybe think about number 21. I think that's a fine one to do as an example. If you, or as a, for participation, if you wanted to chat with me about that guy. Also, number 25 brings back the concept of a one-to-one correspondence. This is a really challenging question, but I like it a lot. I might find a way to, I probably will find a way to bring this thing back up, maybe put it on a review or something like that. So it says demonstrate a one-to-one correspondence between the set of positive integers and negative integers, the set of positive integers and the whole numbers and the integers. And we want to know what does this last correspondence tell you about the whole numbers compared to the integers. If you would like to chat about this question, I would love to chat about it. I'm pretty sure I would happily, if someone figured out this problem, even if they chatted with me about it, I would give them full participation points, regardless of their past history and future history. Because also that would mean you're like watching this video. So I don't know, talk to me about it. That's cool.